Welcome to Module 20 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification bodies of knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing non-normal probability distributions. This module will take approximately 50 minutes to complete. At the end of the module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a Binomial Distributions template and a Poisson Distributions template, both of which are Excel files. The normal distribution is related to continuous data. This means that your data is associated with random variables that can take the form of any of an infinite number of points along an interval. Temperature over time is a continuous type of data. Yes, you might never see the temperature of a room fall below 40 degrees Fahrenheit, but within a range such as 40 degrees and 80 degrees, there are an infinite number of continuous data points if you measure to a high enough degree of accuracy. Remember that discrete data is not continuous in nature. Discrete data is typically about categorical occurrences. In some cases, discrete data can be converted to continuous data to allow Six Sigma teams to use more statistical analysis tools when working with the information. When that isn't possible, however, you cannot use the normal curve or related statistical analysis on discrete data. Discrete data usually involves either a binomial distribution or a Poisson distribution. The normal curve, when presented in graphical format or on a histogram, is typically symmetrical in nature. The data elements tend to concentrate along the center of the curve, with elements fanning out slowly on either side as the curve drops ever towards zero. While a visual inspection of data through graphical analysis can help determine if data might be normal, there are several continuous distribution curves that look a lot like a normal curve. That is why we apply statistical tests such as the chi-squared goodness of fit test to determine whether data is actually normal. Now, don't confuse the chi-squared goodness of fit test with the chi-squared distribution, which we will discuss later. One is a statistical test and the other is a probability distribution. The normal curve is symmetrical and is most commonly required for inferential statistics. It is described statistically using both the mean and standard deviation. While the curve centers on the mean, the number of standard deviations away from the mean changes the probability of the amount of data under the curve. And although the normal curve is the epitome of a perfect process, our data can take the form of any number of a plethora of distributions. So in this section, we are going to take an in-depth look at the different non-normal continuous data distributions that you may face in a Six Sigma initiative. We will cover the exponential, lognormal, Weibull, Cauchy, logistic, Laplace, uniform, beta, gamma, and even triangular distributions, none of which represents a normal distribution, all of which requires the use of continuous data. The exponential distribution creates a histogram or trend line that is exponential in nature. It decreases exponentially as you travel across the x-axis. In an exponential distribution, the data is not organized around the mean, as in the normal probability curve, but at one end of the x-axis. Often, when working with non-normal data, the median is a more applicable data point than that of the mean for graphical analysis. If you locate the median on the x-axis of an exponential histogram, then you know that 50% of the data points fall before it and 50% after it. Exponential distributions are often used when working with data sets that include arrival times, the average or mean time between failures in a process, weight line theories, or the distance in time or space between interesting points of occurrences in data, processes, or experiments. The exponential distribution is particularly valuable when working with certain Poisson distributions. If you recall, Poisson distributions are discrete rather than continuous, which means Six Sigma teams are limited in what statistical tools can be used to analyze the data. At first, the log-normal distribution might appear to be an exponential distribution, but on a graphical analysis, it is obviously constrained by 0. The log-normal distribution on a histogram is asymmetrical, with the trend line appearing more as a wave that moves across the page. The location and size of the wave varies with each data set. Log-normal distributions are often used when working with datasets that describe time durations, such as the time a process or machine is down, or distribution of assets of wealth among the population. Anytime data has a positive skew, which means that the tail of the data is to the right, then a log-normal distribution might be possible. If we only consider the amount of income each household within a population report, almost no household will report an income of 0 or less. In a random sample of income across a city, the data is likely to be log-normal. As you move further right, and the bins represent an increase in income, there will be fewer households that fall into each bin. As you reach the highest bins, you will likely see the fewest households represented. Just to make things more confusing, probabilities can fall into families of distributions such as the Weibull distributions. Data that fits into a Weibull distribution might also fit into another distribution, including all of those previously discussed in this module. Note that the Weibull distributions relate to continuous data, so the data would not likely fit a discrete data distribution. The curves appear to fit the log-normal, exponential, and normal distributions, respectively, even though they each also fit the Weibull distribution. Weibull distributions can describe many data types and are often used when working with reliability applications and failure probabilities that change or vary with time. For example, the chance that a plasma screen will be damaged by burn-in increases both over time the screen is used and over the time that a single still image is displayed on the screen. Data associated with such a concern might feature a Weibull distribution. In a graphical representation, the Cauchy distribution often looks like an elongated normal curve with a tighter peak. While the Cauchy distribution does share some characteristics with the normal curve, the data itself is not normal. In fact, the distribution doesn't have a defined mean or variance, which makes it not useful for many common statistical analysis tools that we use in a Six Sigma initiative. The logistic distribution also appears to approximate the normal curve and is in fact used in some science and math functions to approximate other symmetrical distributions. This is because the CDF of a logistic distribution is more consistently calculable. Remember that the CDF is the cumulative density function and calculates the probability that a given data point is less than or equal to x, where x is any point on the x-axis of a probability curve. The Laplace distribution is often referred to as the bilateral exponential distribution or double exponential distribution. You can see from the image here, the Laplace distribution does seem to be a pair of exponential distributions back to back. A uniform distribution occurs when data points are divided evenly among bins. Exact uniform distributions are almost never going to occur in randomly sampled data, which means Six Sigma teams that see such distributions in data should check the authenticity of the data. Uniformity often points to an error of measurement, problem with the measurement system, a non-random sample, or an issue with the process. In some very specific cases, uniform distributions could point to success. For example, In a manufacturing plant, one machine might make dowels that are used later in the manufacturing process. If the dowel must measure 4 inches for functionality later, and a random sampling of dowels across all time buckets for the machine show 4-inch dowels being manufactured, then uniformity equals success. Like the Weibull distribution, beta distributions can take on a number of shapes and are considered to be extremely flexible. They can become stand-ins for other distributions given certain statistical parameters. Gamma distributions are similar to beta and Weibull distributions in that they take up a number of shapes. In fact, some distributions that aren't covered in this module are actually just more specific forms of the gamma distribution. Gamma distributions are, however, always skewed to the right. A triangle distribution does occur from time to time, and it is formed using the mode and the upper and lower limits of a data set, meaning that when it appears, it is usually as a result of selecting the wrong data for the analysis. A number of distribution curves exist that can be used to visually represent discrete data. In this section, we will discuss those distribution curves. Because discrete data is so hard to work with, statistically speaking, the number of distributions are in fact limited. So, we will talk about the binomial, Poisson, geometric, and negative binomial distributions, as well as when they are applicable to Six Sigma initiatives. A binomial distribution is used when you are dealing with discrete data, and there are only 2 possible outcomes for each trial or sample. In short, binomial distributions relate to attribute data. Yes or no, pass or fail, one or the other. A binomial distribution assumes that the outcome of any given trial is independent of the outcome of another trial. If you flip a coin, it will either be heads or tails. If you flip it again, it will be heads or tails, with a 50% probability for either outcome. It does not matter what happened with the first flip of the coin. In most cases, when considering attribute outcomes, the probability is not distributed evenly between the 2 events, as it is with a coin flip. Instead, there is a probability of success and a probability of failure. For example, if a machine making parts creates defects in 5% of the parts, then you have 2 outcomes for each part made. Either the part will be defective or it will not be defective. A binomial distribution can also be calculated using the binomial distribution probability function. Accordingly, the probability of success times the number of successes desired is equal to the probability of success in each trial to the power of the number of successes desired times 1 minus the probability of success in each trial to the power of the number of trials minus the number of successes delivered, multiplied by the factorial of the number of trials divided by the factorial of the number of successes desired times the factorial of the number of trials minus the number of successes desired. Using the binomial distribution probability, we can calculate the probability that 20 trials will yield 4 defective parts in a process that delivers 5% defective parts. By applying the binomial distribution in this manner to pass, fail, yes, no, or defect, no defect, Six Sigma teams can calculate data that is useful in a variety of real-world situations. The Poisson distribution is often used when dealing with data that is distributed randomly within time, distance, or other unit of measurement. For example, the distribution might be relevant when dealing with calls per hour in a call center, traffic accidents per week on a specific block or street, or the number of defects in a batch. In fact, the word per in a metric is a good indication that the Poisson distribution might be useful. The Poisson distribution can look a little like the normal curve, but it is not symmetrical. This is why statistical analysis is needed, in addition to graphical analysis when working with data. Data can approximate the normal curve on a graph without being normal. One interesting thing to know about the Poisson distribution is that it relates closely to the exponential distribution. Remember, the Poisson distribution is discrete, not continuous. The distribution is an analysis of how many of one thing occurs per another. If data fits the Poisson distribution, you can use an equation to determine the probability of certain events. In using the Poisson calculation, the probability of success times the number of successes desired is equal to the Poisson constant, 2.71828, to the negative power of the mean or average of the process times the mean of the process to the power of the number of successes desired divided by the factorial of the number of successes desired. For example, if a Six Sigma team was working to improve processes in a call center, they might have gathered data that indicates the average number of people on hold for a customer service representative at any given time is 10. Given that information, a Poisson distribution, when considering the number of holds per increment of time, the team can use the Poisson equation to calculate probabilities related to various call scenarios, such as the probability of there being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and even 14 callers on hold at any given time. The geometric distribution is used when there are two possible outcomes for a trial. The trials must be independent from one another, and there is a waiting time before the first occurrence. As with the binomial distribution, the outcome of each trial must be independent. A real-world use of the geometric distribution might include the number of inspections that occur before finding a defective part, or the number of resumes or applications a recruiter reviews before finding the first candidate that meets the minimal job requirements. The negative binomial distribution is also used with attribute data, fail, pass, and other situations where there are only two outcomes for each trial. Again, the outcomes must be independent of one another. The probability of an occurrence must be the same across each trial, just as with the binomial distribution. The negative binomial distribution is often used when teams are trying to determine the probability of a certain number of passes or fails before reaching the predetermined number of passes or fails.